Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into section 6.5 from your textbook, which introduces you guys for, at least for now, the last application of definite integrals that we're going to be studying in our course for a while. This application is going to be extending the idea of the average of a set of numbers to the average for a function. So to do this, we're going to talk a little bit about how you calculate the average of a set of numbers, and then we're going to see how we can use integration to sort of extend that concept to the average for a function. Then we'll take a look at a very important theorem that relates, that sort of tells us what to expect when looking at the average value of a function and how it relates to the function itself, and then we'll take a look at a couple of examples. So, for this, first of all, let's just correctly remember how you calculate the average of a finite set of numbers. So, if you have a finite set of numbers, y1, y2, down through yn, you can find the average by summing those numbers up and dividing by however many numbers there are. So the average of a finite set of numbers is written as y1 plus y2 plus ... down to yn divided by n, since we have 1, 2, all the way down to n different numbers there. Considering that at some point in this class we'll be getting into sequences and infinite series, we'll be seeing a lot of summation notation. So I just wanted to rewrite this y1 plus y2 plus ... plus yn in summation notation so that you guys could just see that. So in summation notation, you could say that this is the sum from I equals 1 to n. So you're letting I be that index. So that index is running from 1 all the way down to n. And then, of course, that capital sigma means you're just summing those things up. Divided, of course, by n, however many numbers you have. So what we're going to try to do in this video is we're going to try to explore how you can extend this concept of an average to an average value for a function rather than just a finite set of numbers. So our real question is how would you find the average value of a function on a given interval? The trouble, of course, is that on a single interval, a function takes on an infinite number of values. If you think about that, right, in any real interval, so any interval, no matter how large or small, even the interval 0 to 1 or something like that, there's an infinite amount of x values in there. And since there's an infinite amount of x values, there's an infinite amount of function values, since we evaluate the function at every real number in the interval. So how do we take basically a infinite number of values and get their average? So our big question, and what we're going to sort of do, is we're going to assume that we have this function f of x on some interval a to b, and we're trying to figure out how can we calculate the average value of this function. So let's sort of explore this idea and see what we can come up with here. So we'll start with our sort of standard diagram. We'll just draw an arbitrary curve. We'll let this be x equals a, and maybe down here is x equals b. And we'll just draw some continuous curve. Doesn't need to really be anything fancy. It's just a generic curve. So there's f of x. And we're working from x equals a to x equals b. All right. Since we, basically doing everything that's related to integration right now, let's try to build some stuff that we're sort of used to with integrals. So let's actually try to take a look at maybe cutting this interval up into some pieces. So let's imagine that we sort of go through and we make some cuts here and we sort of divide the interval into some pieces. We'll do our standard sort of thing and we'll say that the width of each of these pieces is going to be delta x. And then it doesn't really matter if we're doing like left endpoint or right endpoint approximations. So let's just say that we'll call the first one like x1, x2, x3, ... so on and so forth, right? Down until our last one, which if we're doing left end approximations, I guess would be like xn here. And then we're sort of we're going to take the function value at each of these points. So we've got our function evaluated at each of these, and so on. Now, I'm not going to draw in rectangles because we're not really interested in the area under the curve right now. We're just interested in those values there. So, of course, we would have something like f of x1 and then f of x2 and so on down to whatever f of xn, right? Okay, so this, of course, is just a finite set of points because we're just doing an approximation where we're saying, okay, let's look at, these cutting the interval up into these delta x pieces. So we can get an approximation for the average value. So we could say that the average value is approximately f of x1 plus f of x2 plus ... plus f of xn over that n, because we're doing this into n subdivisions. Okay, so this, of course, is just using what we said basically up here, except now instead of saying y1, y2 through yn, we're actually saying we're evaluating our function at n different test locations going along like this. All right, let's see if we can rephrase this a little bit more. Let's see if we can think about n in terms of some of the other stuff that we have listed here, namely a, b, and delta x. If you think about it, right, delta x is the size of the interval, and n, of course, is how many of these intervals we have. So we have this nice relation, right? Especially if you remember your stuff with Riemann sums, you can recall that delta x is actually equal to b minus a over n, right? If you're going to have the interval b from a to b, and you're going to divide it into n pieces, well, then the size of each piece is b minus a divided by n. So we can solve this for n. So we can think about this as n is actually equal to b minus a over delta x. So let's pop that into this expression here. So we now can say that the average value is approximately f of x1 plus f of x2 plus f of xn over b minus a divided by delta x. All right, let's clean that up a little bit by flipping the delta x up out of the denominator of the denominator and put it into the numerator. And we'll take this b minus a and sort of put it out front as 1 over b minus a. So we have that the average value is at least approximately 1 over b minus a times f of x1 plus f of x2 plus f of xn times delta x. So again, that's just factoring that b minus a out front as 1 over b minus a and taking the delta x and putting it up there. All right, so how would we, well, maybe it's time to maybe get rid of this plus ... notation. Let's just write this as a summation so it looks a little sort of cleaner here. So our average value is approximately 1 over b minus a. The sum from I equals 1 to n of the f of xi delta x there. So there we go. There's an approximation for the average value. Now again, we are stuck though with this being an approximation. So what's our standard trick for letting an approximation become an equality? Well, if we take an infinite amount of these approximations, or in other words, if we let that delta x sort of squeeze together infinitesimally thin, then this is not going to be an approximation anymore. It's going to be an equality. So we can say that the average value here is actually equal to the limit as that delta x approaches 0 of 1 over b minus a, sum over all the xi that we'll be summing up, f xi delta x. Then, of course, this limit is as delta x approaches 0, so this 1 over b minus a can just go in front here. And this limit, when it applies to that sum, makes this into a Riemann sum, so we get a definite integral. So we get that the average value here is actually 1 over b minus a, the definite integral. Where are these xi's occurring from? Well, they're going from a over to b. So it's the integral from a to b. And of course, we end up with f of x dx. So interestingly enough, the average value is simply calculated as 1 over b minus a, so 1 over the size of the integral, times the definite integral from a to b of the function. So this is actually a very, very simple expression. I mean, it's basically just applying the definite integral to the function and then dividing by the size of the interval, and that'll give you the average value of a function. Now, this derivation here I think is pretty interesting because it's taking something that you guys have seen many, many times, the average of a set of numbers. People learn that very early on in math, and it's extending it to an infinite set of numbers that happen to be the values of a function. So now we can talk about the average of a set of numbers, but we can also talk about the average of a function on a given interval. So since this derivation was a little messy as we went along, let's go ahead and summarize what we've just derived here. So for this summary, we're saying suppose we have a function f of x, which is a continuous function that just guarantees that you can actually integrate it on an interval a to b. Then the average value of this function on this interval can be calculated as f sub average is equal to 1 over b minus a times the integral from a to b f of x dx. So there we go. That just summarizes the formula we developed on the previous sort of slide there. All right. Before we get into some examples of calculating the average value of a function and really seeing what it sort of means, it turns out there's a very important theorem that relates to this average value concept. So we're going to talk about this real quick, give a brief proof of it, and then get into our examples. So this theorem here is what is called the mean value theorem for integrals. If you remember back from your Calc 1 class or Math 190, you learned a mean value theorem for derivatives, and this one is directly related. The mean value theorem for integral says if we have a function f of x that is continuous on the interval a to b, then there must exist at least one value, x equals c, inside the interval such that the function equals its average value at that point c. In other words, if we were just saying this sort of in English, we would say that the mean value theorem for integrals guarantees that a function achieves its average value at least once on the interval. So in other words, your average value is really a value that your function achieves at least once. Your average value your function passes through its average value at least once on the interval. So the proof of this is actually pretty easy. It uses the mean value theorem for derivatives. So we're going to make use of that. But to begin with, we're going to let capital F of x be an antiderivative of little f of x. So we're letting capital F of x be an antiderivative of f of x. In other words, it's some antiderivative of f of x. In other words, it's some choice of the integral of f of x dx. Notice this also means that capital F prime of x must be equal to f of x. That's what it means to be the antiderivative of a function. So we're going to let f of x be an antiderivative of little f of x. Then we're going to apply the mean value theorem for derivatives to capital F of x on the interval ab. Now, it might have been a while since you remember what the mean value theorem for derivatives says. Well, the mean value for derivatives says that for a function on an interval, the derivative of the function has to equal the average rate of change at least once on the interval. So in other words, for our setup here, we would say there exists an x equals c in a to b such that capital F prime at c is equal to the average rate of change of this f of x function on this interval. Average rate of change would be f at b minus f at a over b minus a. So we're applying this mean value theorem for derivatives, which is something you guys saw and proved in 190, and we're applying it to this antiderivative. Now, this doesn't quite look like the statement back here, but we can actually work to that. What is f prime at c? Well, remember, f of x is an antiderivative of f of x, of little f of x. So big F prime at c has got to be little f at c. So this side here is f of c, f of capital F of b minus capital F of a over b minus a. Okay, let's think about what we can look at this with. Well, we can pull out that 1 over b minus a in front and think about this like that. Okay. And now we're going to use a fundamental theorem of calculus. What is capital F of b minus capital F of a? Well, that's evaluating the antiderivative at b, subtracting the antiderivative at a. That's exactly how you guys do definite integrals. So this tells us that f of c is 1 over b minus a, integral a to b f of x dx. This basically, we normally go this direction. You have something you're trying to do the definite integral of, you find the antiderivative and plug in, but it also works the other way. And what do we have right here? Well, that is exactly what we said is the average value. So we just have f of c equals f average, check. So there we go. There we've proved what we wanted to show. If you want to be really fancy, you can put QED, Latin for quod est demonstratum. That which needed to be shown has been shown. So there we go. We finished our proof there. So this tells us that every function has at least one value in its interval where it achieves its average value, which makes sense. If you're saying something is an average value for the function and the function is continuous, meaning there's no jumps or skips or anything like that, then it should go through its average value at least once. Could it go through its average value more than once? For sure. But this theorem just guarantees that it'll happen at least once. All right, let's get into some examples and understanding really what this average value is doing. All right, so we're going to take a look at a function here. In this case, we're going to look at y equals 1 over square root of x on the interval 1 to 9. We're going to do a couple of things here. We're going to determine what is the average value on this interval. Then we're going to find where the function achieves its average value. Notice that in B, we are guaranteed to be able to do this by the mean value theorem for integrals. And then we're going to try to draw a diagram illustrating these results, helping you guys sort of visually understand what the average value is really calculating. So let's start with A. Should be pretty straightforward using our formula. The f average should be 1 over b minus a, integral from a to b, f of x dx. In this case, we get that f average is 1 over, looks like we're going from 1 to 9, so we have 9 minus 1, integral from 1 to 9, and our function is 1 over square root of x dx. So not bad at all. Now we just need to go ahead and do this. So we get f average is 1/8, integral 1 to 9. Good to probably think about this as a negative fractional exponent, so x to the negative 1/2 dx. Then we can use power rule on this thing. So f average here is 1 over 8. New exponent when we add 1 is going to be x to the 1/2 times the reciprocal, which is going to be 2. And then we're going to evaluate from 1 to 9. So it looks like f average is 1/8. We plug in the 9. 9 to the 1/2 is 3, so we're going to get 6 minus. Then we plug in the 1. Square root of 1 is 1 times 2 is 2. And looks like we get f average here to be 4 over 8, so 1/2. So the average value of this function is 1/2. All right. Well, we know now, to go for part B, that this function has to achieve this value at least once. So how would we find where that happens? Well, we simply set the function equal to its average value and solve. So for B, we're going to take f of c equal to f average. So what is f of c? Well, we just plug in c into that. So 1 over square root of c is supposed to be equal to this average value, which is 1/2. Can we solve for this? Well, for sure, we can do the reciprocal on both sides. Square root of c is equal to 2. Then we can square both sides and get c equals 4. So that means that at x equals 4, we achieve average value of 1/2. So at x equals 4, and you can just check manually, at x equals 4, 1 over the square root of 4 is 1/2. So this achieves that average value. Is x equals 4 in our interval? For sure. The interval is from 1 to 9, so 4 is definitely right in there. Okay, now let's try to draw a diagram illustrating these results here. So we'll start by just sketching sort of our curve on this interval. So give ourselves a little bit of space there. So there's 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then we've got 1. We'll just put maybe, let's call that maybe 1/2 and 1 to make it a little bit easier. 1, 1/2, and 1 there. Okay, so let's try to go ahead and draw this. We're drawing in 1 over the square root of x. So we know at 1, 1, we've got a value there. And then we know that at 4, it's going to be at 1/2 right there. And then at 9, I guess it would be at 1/3, so something like that. And then to actually draw in our curve, I guess it should look something like that. There we go. So there is our actual curve, y equals 1 over square root of x. Perfect. Okay, Now, let's indicate what our results were. It actually turned out to be one of our easy sort of points. So there was our x equals 4, and there is where it achieved its average value. Okay, now, let's think about a little bit more about exactly what we found here. I mean, certainly this 1/2 does seem to sort of be in the middle. I mean, the function is as high as 1 and gets as low as 1/3, but it means a little bit more than that. So to think about that in sort of a graphical way, right? So to understand f average in a graphical way, we should basically take a look at this formula and think about rearranging it a little bit. I mean, this is the formula you want to use every time you want to calculate f average. But when we think about it visually, it might help a little bit to bring this over to the other side. So f average, if we think about it, is really f average times b minus a is equal to the integral from a to b f of x dx. Now, if you think about that, what that's really saying is, on the right-hand side, that's the integral of our function from a to b. So that's the area under the function on this interval. In other words, in our diagram, it would be all this stuff. What this is saying on the left-hand side is that if we do f average times b minus a, we'll get the same area. So in other words, we're saying if you were to build a rectangle that has a height of f average on the same interval, that would have the same area. So in other words, if you imagine sort of visually drawing in a rectangle that's got this height at f average, then this area in here is equivalent to the area under the overall curve. So I want to sort of sketch that in so that you guys can sort of see that. So let's go ahead and draw a rectangle over this interval that matches with our average value here. So I'm going to go ahead and just draw that over to there. And then down to here. Notice I'm not drawing obviously all the way to like the y-axis because it's going to be just on our interval. Okay. And there's my rectangle. So one way of understanding the sort of average value is that the area in this rectangle is the same as the area under the curve. If you prefer, you can think about it a little bit more as sort of basically being able to see that this stuff here, the stuff that is above the average value, the area of the stuff under our curve but above the average value, is actually identical to this stuff here. In other words, that the red area equals the green area. So in other words, average value finds the exact point, whereas if you took all the stuff that was above that, in area, it would be exactly the same as all the stuff below that. So a good way of visualizing it is to sort of draw in a rectangle at the average value and then recognize that any area above that but below our curve is equivalent to any area that's below that average value but above our curve. You can also sort of think about it that if this stuff was like sort of a spongy, like manipulatable, able to be manipulated material, you could take this red area here, sort of cut it off, squish it in, and it would fill in exactly this, forming a rectangle that has the exact same area as what was originally under our curve. So that's just a nice way of sort of visualizing what we're really calculating when we're doing the average value. Notice also the average value does not necessarily occur at the middle. On the interval from 1 to 9, right, the middle of that interval would actually be at 5, right? That would be the actual middle, but that's not where the average value occurs because, again, it's based on finding that exact tipping point where those areas are equal. Okay, let's go ahead and take a look at one more example of doing this. So we're going to have another function here, y equals 1/2 x plus 1 cubed. On the interval from 0 to 4. We're going to do the same thing, calculate the average value, find a value in the interval where we achieve that average value. We know there has to be at least one, but we'll go ahead and find it, and then we'll try to draw a diagram of that as well. So let's go ahead and do the average value to start with. So again, average value every time we want to do this, 1 over b minus a, integral from a to b, f of x dx. So we can plug this stuff in. F average is going to be 1 over 4 minus 0, the integral from 0 to 4, 1/2 x plus 1 cubed dx. So there we go. Now we just need to go ahead and actually evaluate this integral. So we've got 1/4 times the integral from 0 to 4, 1/2 x plus 1 cubed dx. Now, a couple different ways you could evaluate this integral. If you're feeling like you want to do a bunch of messy arithmetic and algebra, I guess you could FOIL out 1/2 x plus 1 times 1/2 x plus 1 times 1/2 x plus 1 into some cubic polynomial and then integrate. Much easier since this is linear in here. This is just a linear term, 1/2 x plus 1. We can just get away with a nice, easy u substitution. So let's go ahead and let u be 1/2 x plus 1. du would be 1/2 dx. We don't have 1/2 dx, so we could get 2 du is going to be dx, so we're going to get an extra factor of 2. And we can change our bounds. Original x bounds were 0 and 4. The new u bounds, when we plug in 4, 1/2 times 4 is 2, plus 1 is going to be 3. When we plug in 0, 1/2 times 0 is 0, plus 1 is going to be 1. So we can get the f average here is going to be 1/4. The integral from 1 to 3 now, u cubed times 2 du. Now that is much easier to do. We can bring the 2 out and just cancel it with that 1/4. So we have f average is 1/2 and then 1/4 u to the 4th evaluated from 1 to 3. So that's nice and easy there. So f average is 1/2 times 1/4 times 81 minus 1/4. And that looks like we're going to get 81 minus 1, which is 80, divided by 4, which is 20, divided by 2, which is 10. So we get an f average of 10 here. So the average value for our function on this interval is equal to 10. All right, let's go ahead and find where our function achieves this. So let's go ahead and we're going to take f of c equal to f average. F of c, of course, is just 1/2 c plus 1 cubed, and we're going to need to set that equal to 10. It's going to be a little bit messy here. We're going to get 1/2 c plus 1 equals the cube root of 10, which is not ideal, but that's okay. 1/2 c equals the cube root of 10 minus 1. And if we multiply by 2, I guess we get 2 times the cube root of 10 minus 2. So we achieve our average value at this sort of weird 2 times the cube root of 10 minus 2. Now, obviously, we can just leave it sort of exact like that. There's nothing wrong with an exact answer like that, even though it has that sort of cube root in it. But considering that we are going to sketch a graph, it might not be a bad idea just to get a sort of rough approximation of what that sort of size of that value is. So if you have your calculator, you can actually go ahead and figure out an approximation for that. 2 times 10 to the 1/3, and then minus 2. Just for drawing purposes, probably not a bad idea to just realize, we'll just put this in sort of note here, C is approximately, I'm getting about 2.31. Notice as a quick check, that is definitely inside the interval 0 to 4, so that we knew had to happen there, right? Because that's what is guaranteed by the mean value theorem for intervals. This C value, at least one of them, has to be in the interval there. That also just brings up another sort of little point. If you guys are ever solving this and you get several C values, that's fine. Just make sure you throw out any ones that are not in the interval, because we are only interested in ones that are in that interval. All right, let's go ahead and draw a diagram for the results here. So I guess we can just sort of squeeze that in here for C. So again, we'll sort of focus over here because we know we're working on 0 to 4. So I guess for my x, we'll just do 1, 2, 3, and 4. Quick check though, we're going to need a pretty lengthy axis in this direction. I guess if I plug in 4 into that, I'm getting 2 plus 1, which is 3, and then cubed is 27. So I guess maybe I'll just go by like 5s or something. So there's 5, 10, 15, 20, 25, and 30. So there's 5, 10, 15, 20, 25, 30. And 1, 2, 3, 4. Okay, so let's go ahead and draw this thing at x equals 0. We have 1 cubed, which is 1. So we've got something way down here. And then at x equals 4, we know that we're going to get 27. So we get something way, I guess, here. And then, of course, we also know that at about 2.31, so somewhere right in about here, right, we also achieve 10. So we've got something, well, I guess, roughly right about there. And even though this thing is a little bit weird, do keep in mind that this thing is just a cubic. So on this point, it sort of looks like that sort of polynomial type shape. It's getting steeper and steeper there. All right, so there we go. Now, let's try to actually illustrate what's going on here. So we'll draw in our little rectangle over this interval. So if we draw a rectangle that is on the same interval at the height of the average value, so there we go. Okay. Then this area where our average value is overestimating our curve, this stuff in here, that area there, has to match identically if we look at the area where our average value is underestimating our curve. So this stuff right in there, this area here, those two areas, the red area equals that green area. So in other words, if you wanted to, you could think about taking this stuff here. You could then smush all of this and it would fill in this exactly, and you could build a rectangle with the same base at the average value that would give us a rectangle that has exactly the same area as the area originally under our curve. So this is a couple examples for you guys. Hopefully, calculating average value should be pretty straightforward. Finding where you achieve the average value is simply just an algebra question. The only thing that maybe is takes a little bit of time to get used to is trying to visualize and understand the relation between the average value and the area sort of below that average value and above our curve here, versus the area that is above the average value and below our curve in this case here, and how the average value is the perfect tipping point where those two areas are equal. This wraps up section 6.5. This is a relatively short section here. The next video will be moving into section 7.1, which means we'll begin our investigation into techniques of integration. So we'll be moving away from applications of integrals and instead focusing on some better ways to actually integrate functions.